Hello, you guys hear me? Excellent. So I'm Greg Sowell, and this one's going to be about high availability with MikroTiks. So some of the concepts you cover, you can extend by adding wireless onto it. I'm really just kind of focusing on the wired, but you can layer other things on top of it. So you always got to start out with a de facto, who am I? Greg Sowell, I've got some certifications. I grew up Cisco and ran away as fast as I could over to the MikroTik camp. I was trying to build a lab, and I just couldn't afford the gear, but man, I sure could afford the MikroTik stuff. So I'm VP of Technology for a data center group. I do a little bit of consulting, not a terrible amount. I'm now an author for lynda.com, which I'm kind of proud of. And then also president of a company called StrayaNet now. So one other thing I'm kind of proud of is this group of guys I have together called the Brothers Wisp. There's a whole lot of names on there. Andrew Cox is actually here from Australia. Andrew Thrift from New Zealand couldn't make it, but he sent some emissaries. I saw him earlier, really spiky hair. Thomas Kernak from Slovakia. Tom Smith from Ireland, he's here. I'm sure you guys are going to groan in his presentation later. Mike Hammett from Chicago couldn't make it. JJ Boyd, North Carolina. Alex Hart is sitting right over here. Justin Miller's somewhere in the room, I saw him, and then Wilson is here as well. But it's just a podcast talking about ISP side of things, and it tends to skew towards the wireless. So StrayaNet, MDU ISP, using the tremendous bright Wi-Fi system. Support all the way down to the end user, so if you guys can get me IP, I'd be happy to do support at these different apartment complexes, completely customizable interface. Profit sharing on the MDU, give me a shout. So let's get to the meat. Assumptions that you're going to be somewhat familiar with the MikroTik interface, probably Winbox. I'm going to show Winbox. I have CLI stuff up in the end. I've got a zip file with all the CLI commands associated with it, but most of the folks here want to see Winbox, so I'm giving it to you. Adding addresses, static routes, a little bit of knowledge of dynamic routing is not going to hurt you, but we're keeping it pretty basic. This is going to be a basic one. Last time I did a really super technical one, and I think it applied to like 4 people, so this one's casting a wider net. So what is high availability? In simplest terms, a system or component that is continuously operational for a desirably long enough length of time. In essence, just trying to maximize your uptime in your network, right? Just trying to keep things online and available. So number 1 for me is change control, and it's probably the least followed thing for a lot of wireless ISPs. Something I was told a long time ago, if you want to be big, you have to act big, right? So start adding these policies. So number 1, if you're having big impacting things, do it in a change window at a specified time, right? Generally not when it's going to hurt everybody. Notify customers, and I put an asterisk for major changes, right? If you're doing small manipulations that quote unquote shouldn't affect them, there's no need to make them panic. I don't know how many change windows we've had, which we ended up canceling, and then we get all these calls the next day about, hey, I'm having all these problems with these different things. I'm like, well, obviously it wasn't due to my change window because I never actually performed it. So don't incite a panic if you don't have to. Create a change procedure document, right? Add all the steps you're going to take in your config changes, add the intermediate steps you're going to do to test. I'm going to ping these things. I'm going to check this route server. I'll look at these looking glasses, right? And then also have a backout procedure. If none of this works, let's roll back to a steady state, right? So I've seen some people make all these changes and they forgot where they started, and it's impossible to roll back. And then also have a second set of eyes approve it. Have somebody else just read it over. I've been countless times where I've been stuck on a problem for 30 minutes. Somebody else looks at it in 5 seconds, they know what the problem is. So second set of eyes never helps. And the last is follow your policy. If you're going to create it, go ahead and follow it. There is something called break fix, right? If things are broke, change control goes out the window and you fix it. But other than that, try and follow your policy if you have it. Another big one is backups, right? All this stuff is common sense. Maintain regular backups. So I wrote this super ugly backup script, and I put it up on my website with a code 1,000,000 years ago that from a Windows box will just go out and daily download all of your configs. There's scripts on the wiki for setting up a little script in your MikroTik where every night it will email a backup copy of the config to you. I've seen there is some rancid integration where it will daily go out and pull and do kind of a diff thing. None of the rancid integration is simple. The email backup is somewhat simple, but you have to comb through. Thomas Karnak actually just created well, he didn't just create it, he just released it, a program, and I hope I'm pronouncing this right, Unimus. It's an automated backup system that will connect to your MikroTiks and does revision control, all this really cool stuff. He's a huge NetXMS fanboy, and so it integrates directly with that. We'll pull all of your devices out of there and automatically back them up. I've got a link here and towards the end, so you should definitely check it out. Spares, keep a spare on the shelf. If you guys are WISPs, you know you get hit by lightning, you get hit by surges. Especially if you're using MikroTik equipment, it's cheap enough where you can have a little bit on hand. Make sure you have one. But beyond that, if you're going to test something, I really recommend, especially any of the things you see me doing, test in a lab environment first. If you have spares of your actual production equipment, you can test these things and see how they're going to react in your environment. Especially when you're updating code, you move to a new code train, be sure to test all of your features and functions, at least the core ones that you really require to stay up. Make sure that they're going to act in a predictable manner that you're expecting to happen. Also, occasionally you'll get called by a customer for an emergency build out. You got some spare on hand, you're ready to go. Let's see, what else? Backup power, right? UPSs, all of you guys throw a UPS in the can, I'm sure, of some sort. I've seen some guys go as far as to just put a car battery and rig it to an APC, and if that keeps it up, all the better. Dual power source devices. So MikroTik is fortunately starting to actually produce some gear, like the 1072 that's got dual power supplies. Or if you're running it on an x86, get something with dual power supplies. Pretty straightforward. Something I've seen some other folks do with like the 450G, they do have the DC barrel jack, so you can power it that way. But then from a different power source, you run a PoE into Ether 1. So if either of those fails, it'll pick up and be powered, which I thought was really clever. So moving into some actual configuration, I didn't exactly know where to start on which sort, so I started with bonding and LACP. So bonding is pairing multiple interfaces together and kind of having them share the load in one form or fashion. So MikroTik has several algorithms you can move from. I like to use LACP because it's standards-based, 802.3 AD. So if you're going from a MikroTik to a Cisco switch, you want to use LACP. If you use balance round robin, the Cisco switch is going to see that MAC address flapping from multiple ports, and it's going to freak out. It's going to lose its mind. So you don't want to do that. If you're going from a Linux server to a MikroTik, it's usually best practice to go ahead and do LACP because everybody's implementations are a little bit different. So try and stick to a standards-based if you can. Traffic sharing is one of the main features of this, right? So there's different hashing algorithms you can use. So it can be layer 2 based, so just max, or layer 2.3. And I think you can go 3.4, so you can add some TCP ports. So it'll kind of distribute the load amongst all these interfaces, right? So it gives you some additional bandwidth. But if any one of those interfaces, say in this example, you have 3 interfaces here that are all bonded together. If one of those fails, the traffic will just switch over to the remaining interfaces, right? So that's a little bit of redundancy you gain in there. So you get performance boosts, but you also get a little bit of failover capability. So if those interfaces go down, and you can lose 2 of those interfaces, and it may be degraded service, but you're still maintaining connectivity. And ultimately, that's what we're looking for, right? Something is better than nothing at all, even if it's a little shaky for a bit. So let's take a look at it in action. Come on, video. There she goes. So I'm not brave enough to do this live, so here's a video of it actually working. So this is configuring the router 1 from that diagram. So interfaces, bonding, then you just specify 3 that you want. We're going to change the algorithm to 802.3 AD, just leaving everything default for funsies. Throw in an IP address on the bonding interface itself. 192.168.1.1. Then you just select bonding. Then we can go tools, ping. And so this is pinging the other side of the link of those 3 bonding interfaces. I'm going to switch back over and look at the individual Ethernet interfaces that comprise this bonding. And so you can look at the bandwidth graph so you can see which interface. So it's using Ether 3. So we can fail Ether 3. You'll see the ping hiccuped once and just switched over to Ether 1. Then we can kill Ether 1. Ping hiccuped once, and it used the remaining interface. You can see it's actually pretty fast, pretty quick convergence there. You bring it back up, you have to wait for it running status, so it's back in the LACP group, so that we can fail that middle one. So you can see this is actually pretty quick, pretty snappy. And then I just kind of keep switching them around, flip-flopping them. You can see they actually run back into the LACP group and come up as running in about 1.5 to 2 seconds. So if you do have an interface flap, it's going to come back pretty quick. So moving on from that is going to be next hop redundancy. So if I'm on a subnet and I'm a user, say your server infrastructure, something you could do is add multiple default gateways, right? Next hops for these server infrastructures to leave. That way you could lose one router and you're still maintained from the opposite side. So in this example, we're using VRRP, Virtual Router Redundancy Protocol. You can have just 2 routers. You can have 3 routers, 4 routers, right? You can add multiple. I've never seen anybody use more than 2. I'm sure there's special use cases where you can go up to 5 if you wanted to. One router is chosen as master, so there's basically a floating IP address, and there's a specialized MAC that's actually created to advertise the specialized IP address. The 2 peers, right here, say router 1 and router 2, they'll actually share that virtual MAC address. So it will move back and forth between them. So one guy will determine he's master, and he'll take that MAC address. If for whatever reason he fails, the other guy will pick up and take that MAC address over for him, as well as that IP. So that default gateway will swing back and forth between the 2. So the election process is there's a VRRP priority, starts at 100, and higher priority wins. So if you have a higher priority, in this example, router 2 has priority 105, so he's going to be master. Otherwise, it uses whoever's got the highest IP address physically configured on their interface. So floating MAC moves over to Ether 2 because he has higher priority after the negotiation, and then you'll use him as your default gateway. If he fails, kicks over to the other guy. So, excuse me, VRRP has this concept of preemption, and it's on by default. So the idea is if I come up and I have a higher priority and somebody else is master, I'll go ahead and communicate with them and I'll take that master role back over, right? So since preemption was enabled, he went ahead and took master ownership back over. So again, due to my chicken nature, here's a video of us doing a configuration. So whenever you're adding the IP address, both routers are going to be in the same layer 2 subnet. You actually have to connect them via a switch because they communicate over that layer 2 subnet to each other. So we're going to add an IP straight on the interface. Then we're going to create the VRRP interface. Tell it what its main interface is. Added the priority 105. You see it's not up because we haven't added an IP address to the VRRP interface itself. The IP on the VRRP interface is going to be a /32. So it's just a host address that sits in that subnet. Whereas on the actual interface, you're going to put the subnet mask. So it's a little bit different. You give it a second, it's going to realize, hey, I've got an IP. You see how it's not valid until he went to running. Now that he's the running master, the IP address is valid now. Goes back into use status. So you can look, this is the secondary router. He's negotiated and become backup. So we're going to come in, we're going to do a couple of pings, and we'll test some failures. So this is my test host. So this is a PC on the network, and he's pinging that virtual MAC address, the .1. Come over to the master. We're going to disable that Ethernet interface. I had to think about it for a minute, but then I came to the right conclusion. You can see it fails for a couple of seconds when the other guy takes over the master role. So pretty snappy there. You see this is the secondary guy. He's assumed the master role. His IP address is valid. We're going to come back over, re-enable the interface. And again, this is where preemption kicks in. So router 1 has the higher priority. So he's going to seamlessly assume that IP. So before, you saw there was a hiccup in the network because for a second, that MAC address was no longer available, the default gateway wasn't there. The other guy has to think about it, ensure that the other one has failed, then he'll take over. Whenever preemption occurs, it's seamless because both hosts are available, so he's going to come up as master immediately, and it's just going to quickly kick back over. So one feature request I have for VRRP, I know this isn't the venue they like them to come out in, but interface tracking with priority decrementation. Right? So if we kind of kick back here to this diagram, imagine, if you will, router 1 at the top of him has an internet connection or a connection further into our network, and router 2 has the same. If you have interface tracking or tracking objects like some other manufacturers do, I can actually watch multiple interfaces. As those outside interfaces go down, it'll decrement a counter and his priority will lower. So if the outside interface for router 1 goes down, router 2 will see that, he'll take over the master ownership, right? So you can track multiple things, which is really handy. So if you're doing VRRP on the outside and on the inside, if the outside VRRP fails, the inside has no visibility to that. So if we added tracking options, we could see that and then kick over. I know you can do that with scripts right now, but it's kind of, it's not built into the system, so it's not as efficient as it could be. So I'd really love to see that become kind of part of the standard config. So moving on, something really simplistic. It's not even that complicated as a fancy protocol is just floating static routes. And it's the idea where you can have two routes, say two default routes is usually what you see it used as, pointing to two different destinations. You raise the administrative distance of one, right? So the AD value is associated with routes and how they're learned. And it's really the trustworthiness of a route. So where did I learn it from? If it's directly connected, it gets a 0 because it's most trusted, because it's configured right on the router. If it's a static route, I manually put it in, so it's going to give it a 1 by default, right? Next trusted. And as you use different protocols, they get values ascending up. So the lower it is, the more trusted it is. So you can add two static routes, have one at the default 1, and then you add one as a 10, right? So he's not going to be used unless the original 1 were to fail, the more trusted. So here's our example again, router 1, 2, and 3. You can see the active path is going to the left because he's using AD1. So in our route statement, we're actually going to use the check gateway feature, which does a ping. So it'll ping what you have set as the next hop. So it's actually going to ping 1.2. If 1.2 does fail a ping, or if that interface goes offline, either one of those, it's going to kick over to Ether 3 because it's going to invalidate that original default route. There's a big red X. That means it failed. It goes over. And then whenever the path returns, that route will get installed back into the route table as valid, and it'll move that direction. Let's see, dynamic routing. So this is where it gets a little bit more complicated. Using OSPF or BGP or Vrrp, don't use Vrrp, it's very inefficient. But dynamic routing works much like the static routing does. Only instead of manually putting in routes, it efficiently communicates amongst multiple routers and will find the best path through the network. I'm going to just kind of do a quick and dirty demo of OSPF, right? So if you have a highly redundant network, you could do all this with static and failures, but you can only look one hop away, really, so it gets a little bit more complicated. With dynamic routing, they're actually going to communicate with each other, share routing information, and pick their best path based on what they've learned from their peers. So if there's a failure, it'll reroute around. It may not be the most efficient path, but some path is better than none. Let's watch it work. Maybe. There it goes. So again, we're going to be doing configuration on router 1, 2, 3, and 4, already assumed to be working. I created a bridge interface and named it loopback1. If you create a bridge and don't add any ports, you can use that as a loopback, which is really convenient. That's what we're going to be pinging here in a second. So this is very simplistic. You would want to highly tune it. You go to networks, you add an IP address. Some people think this is how you get subnets injected into OSPF, and while it does that, this is truly how you turn on OSPF on an individual interface. Whenever you add a network address into an OSPF network statement, it says run on these interfaces that cover these IP addresses. So we're giving it a second to kick up. You see the other peer come on. So you have router 2 and 3 connected. We're going to do a couple pings in a second. You can see that our 2222 address, which is a loopback all the way at the very top, is available. Do a magical ping. And then we'll go in and fail an interface in just a second. Again, just back to the diagram to kind of give you an overall idea of what we're about to fail. So this is router 2. We're going to fail that interface. We'll kick back. And you see there's a quick hiccup. Then OSPF rerouted around. Come back to the routes. You see some of those neighboring routes that used to be there disappeared. Right? It's all pretty simple. But again, I would say definitely test all this in a lab environment before you run it in production. Because for brevity, I've actually clipped out some of the video while it reconverges occasionally. So it may seem a little bit faster than it truly is in real life. All right? So it gives you the ability to fail individual portions of your network. So these routers and these diagrams, they don't necessarily have to be hardwired to each other, right? These don't have to be router-router physical connections. These could be wireless links, right? This could be across a building. This could be a 5-mile shot. This could be a 10-mile shot in between towers, right? So this is a very common tower configuration where you have a router running OSPF at the base. You have radios going up that are actually doing the transport. So you can keep your transport layer 2 and keep routers at the base. It's fairly common practice. So there's another little tricky protocol that exists called bidirectional forwarding detection. It's basically a hello protocol. 2 routers will communicate using UDP, it's like 3754 or something like that, to each other. And by default, it's sub 2-second detection of a failure, but you can tune it down to be sub-second. So within a second, you can actually detect, and it supplements OSPF or BGP. So it gives you the ability to say, hey, this OSPF link, it's actually running BFD, watch BFD. If BFD communicates that there's a failure, go ahead and immediately fail those routes out. So it's just a really snappy method. It also works with BGP, which if you're transporting BGP, default timers on a BGP section are 60-second hellos. So if the transport, the layer 2 breaks in between and the interface doesn't physically go down, your router doesn't realize this peer's gone until 3 minutes pass. And so for 3 minutes, you could be blackholing traffic. So BFD can actually give you, I wouldn't really suggest doing sub-second with BGP, but something close to that. It can give you pretty quick failure detection over a transport link. Highly recommended. So in this scenario right here, you've got switches in between. So if either one of those links between these 2 routers were to fail, your routers aren't going to realize that right off the bat because their interfaces didn't flap. BFD actually gives you the ability to, since it's communicating all the way through, sub-second realize that and then fail over. So here's kind of a quick, dirty example of BFD in action. So I'm going to simulate a failure link between that. I actually did this config maybe last night. So I simulated the switches with just firewall rules. So going into BFD, you can see there's no neighbors listed, but we have default values already in there for all interfaces. So we're going to create an OSPF connection on this single link. So we're adding the 2 networks in for my loopback and for my directly connected. We're going to go to interfaces. I'm going to edit it. And I like to just let it dynamically create, copy, check, use BFD, okay. And so now it knows to assume my neighbor is using BFD, wait for it. As soon as OSPF neighbor comes up, boom, there he goes, we're getting routes. You look back down and now BFD is actually enabled. So you're not going to see anything there until you attach it to a protocol. So you're looking for state up. 4, 5, excuse me, 5th column over. And so I've got this firewall rule that blocks BFD messages only. So we're going to enable that, then kick back over, and you see it went down, and then to a NIT. A NIT's the loading state. So you saw how fast it actually went down and pulled those routes out. It was almost as fast as I could go back. So if I disable that rule and cut back, you can see it comes up even before I can tab back over to that interface. So BFD is operating very quickly. And again, I chopped out a little chunk of time there for brevity because OSPF doesn't necessarily come back up that quick and then become adjacent fully. But you saw the routes pop back in the table. So BFD for sure is a very quick way to pull down. Whenever it does come back up, OSPF is still going to take some time to reconverge and do all the things it needs to do. But one last thing, come shake my hand, tell me your story. You guys, I learned the most interesting things from you. I don't drink, but everybody else I know does, so be sure to buy them a beer. I guess thank you guys for coming. Just the last little bit of link to the resources towards the end. Any questions or anything?
Okay, thank you, Greg.
Absolutely.
Questions?
Hey, Greg. Two-part question. One, on the bonding, is there a way to specify which, I was thinking about using it maybe for redundancy on wireless links on backhauls. Is there a way to specify, use this route over that route, as I'm doing with OSPF?
For bonding?
Well, you were showing the bonding earlier, where you were bonding like, 4 or 5 Ethernets. I was thinking bond 2 backhauls, so I have failover. But one's a gig and one's, say, 200 megs. I want to go to the gig link.
So in bonding, there's I'm sorry, let me use this. In bonding, there's an option where I believe you can, I think active and then failover. So I think you can actually choose which one's going to be, I believe you can choose which one's going to be active.
Okay. And the other thing is, when tuning OSPF over long backhauls, 5, 10 miles, would you recommend using BFD and maybe making your timer higher or lower, or what would help? I get timeouts every now and then, under really high load, and
it can be
stuff goes down and comes back up. It's like, oh God.
Right. So imagine, if you will, a wireless link flaps for 1-2 seconds, but comes back. So your OSPF never actually realized that happened. So the link stays up and connected. If you have BFD, it's going to see that and it's going to tear it down. So if that link starts just kind of incrementally flapping a little bit, your customers may not see a tremendous amount of loss, but if you're actually implementing BFD, it's going to kick it down really quick, and it's going to take a little while for OSPF to come back. So it can be a little dangerous, I'd say.
When you talked about the redundant default routes scenario for using a check ping, does that actually use a local traffic method to where it just uses Ethernet to check that IP address?
So if you're using, say, Ether1, whatever IP address you have bound there, it's going to be sourced from that IP and it'll ping out. So I can tell you in some lab testing, I've seen that check ping command take 1.5 minutes to 2 minutes to realize that far side actually went down. So that's not necessarily a very fast, foolproof sort of option. NetWatch is another thing you could do. You could do a NetWatch script and have that script, disable the route a little bit quicker. But then there's you have to have like a static route associated with going out this. So one thing you can do is, let's see, say you have 2 internet connections. Let me just find one of these. This will work. Say you have 2 internet connections. Router 2 has an internet, router 3 has an internet. And for funsies, you could say add a static route in router 1 that says 4.2.2.2 lives out router 1. Just that one host, and then you could do a NetWatch that pings that. So even if you disable the default route, it's still going to try and go to 4.2.2 this way. So whenever that internet connectivity comes back, your NetWatch can realize that and then re-enable the route. But say, for example, they're doing maintenance on 4.2.2.2, then that could cause problems. Yeah.
Okay, thank you. Next question.
2 things. You don't want to pin up DNS like that with a static route, because if it does fail, maybe half your clients can't get out to the internet because DNS isn't working. Had that happen before. And the second thing is VRRP. When you set that up, and let's say you have that on your edge routers, how do you implement OSPF with that? Do you make adjacencies to your VRRP IPs, or do you do it to the interface IPs, or you just use that on your WAN side for BGP and that kind of thing?
Most of the VRRP I use is handing off to customers, right? So they want a redundant connection, so I'll have two pieces of equipment that I can hand off to them, right? It goes into their switching infrastructure. Hopefully they add 2 switches, right? If you have 1 switch, then what's the point of taking 2 feeds from me? But it just gives you a little bit more resiliency upstream of your network. I can more confidently give a higher SLA if I'm giving them 2 routed interfaces. So I don't OSPF into any of my customers because I don't trust them. And frankly, neither should you guys. If you're going to do something, do BGP and do some heavy filtering if you have to. That's normally my typical application, if that works.
Okay, thank you. Last question.
Greg, and this might flow into that last question. If you use VRRP and say you've got a lot of VLANs and you've got 2 like routers on a stick, is the only way really to implement that is to put VRRP on each VLAN interface to make that work properly?
Yeah, to my knowledge, that's how it's designed. So it wants to be on kind of a so layer 2 failover. If you had, so you're talking about 2 routers with 2 router on a sticks with the same VLANs. I'd have to think about that, but I think the default would just to be to on those VLAN interfaces run different instances of VRRP on each one of those. Otherwise, you could be getting into some kind of crazy loopy stuff, like spanning tree loopy sort of that thing. Not like crazy.
Okay, thank you, Greg.